Okay, so here we're given a problem where we have to factor a polynomial completely. So you can see we've got a four-term setup here. And as with many general factorization setups, a lot of potential techniques could apply to a situation like this, and basically you just apply techniques until you can't apply any factorization techniques anymore. So with any general factoring procedure like this, your best strategy is to first try to take out a greatest common factor from all the terms at once, if there is one. So if you scan through this, you won't be able to take an x out because you don't have any x component in this term here, but you can at least take out the leading negative. Again, remember, if you've got a leading negative on your polynomial, always factor that out along with any greatest common factor there is. And along with that here, you can see that there is a greatest common factor to all these terms, and it's a 5. So we can take a minus 5 out, so that'll flip all the signs from the original problem and get rid of all the 5's basically. So taking minus 5 out of everything leaves behind then an x to the 13th power, then minus an x to the 9th, then plus an x to the 4th, and then a minus 1. So there's what's resulted now from finishing off that first key step of taking out your greatest common factor. And you really do want to do that first because it'll make other factorizations potentially more apparent as you go through with the rest of the problem. So here in this case, you'll look at now what you've generated after having successfully completed one stage of the factorization. And here you've got a polynomial with an even number of terms greater than or equal to 4, in fact exactly 4 here. So in a case like this is a situation that might yield to a grouping. So take your 4-term polynomial there, break it up into a couple little groups, and see if you can get greatest common factors out of each of the 2 little groups here. So when you apply that in this particular case, well, the minus 5 that you've taken out, that monomial is done. You're never going to be able to break that down any further. But when you look at the 4-term polynomial setup here and perform little greatest common factorizations on each little group, the first group here has a common x to the 9th in it. So you pull out that x to the 9th, that leaves behind an x to the 4th minus 1. And you'll notice now that that's exactly what's just waiting and ready to go in the second little group. So for the sake of completeness, if you want to officially factor out the plus 1 that really does nothing, you've got a plus 1 times the leftover x to the 4th minus 1. And now this is a sign of a successful grouping. You've got exactly the same leftover factor in each of the now 2 big terms in the set of parentheses there. So you can factor that x to the 4th minus 1 out as common, so there's the minus 5 we took out in the beginning. Here's the x to the 4th minus 1 that factors out, and leaves behind then to complete the grouping an x to the 9th and a plus 1. So there's the grouping actually fully complete. We've gotten as much mileage out of that grouping as we can get. So once you finish a stage in a factorization process, always look at the factors you've generated and see whether those factors can be factored down any further. So again, running through the list here, minus 5 is as fully factored as it's going to get. You can't do anything else to a monomial. But now look at what you've got remaining here. You've got an x to the 4th minus 1. Well, that's a difference of squares because there are 2 things, namely x squared and 1, that you perfectly square to get x to the 4th and 1. So you've got a difference of squares factorization appearing here. And then when you look at this x to the 9th plus 1, this is in fact a sum of cubes because the 2 things you perfectly cube to get x to the 9th and 1 are x cubed and 1. So there's going to be a little more factorization with each of these. So if you start out and apply the factorization formula for this difference of squares. A difference of squares factors is the sum of the 2 things being perfectly squared times the difference of the 2 things being perfectly squared. So in this case, that's x squared plus 1, the sum of the things being perfectly squared, times x squared minus 1, the difference of the things being perfectly squared. And now when you look at this sum of cubes that we've got here, remember that a sum of cubes factors as a binomial times a trinomial, where the binomial, well, first off carries through the sign in the original sum or difference of cubes. This was a sum of cubes, so we've got a plus carrying through here, and then that sign is bookended by the 2 things that are being perfectly cubed to get you x to the 9th and 1. Well, the thing, as we noted, that you perfectly cubed to get x to the 9th is x cubed, and the thing you perfectly cubed to get 1 is 1. So there's the binomial part of this sum of cubes factorization for x to the 9th plus 1, and then remember that that generates a corresponding trinomial based on a pattern built from the terms in the binomial. So remember how this goes. The first term in the trinomial is the square of the first term from the binomial. So the square of the first term from the binomial is x to the 6th, x cubed squared. Then opposite sign from the binomial, product of the two things in the binomial. So the product of x cubed and 1 is just x cubed. And then finally you add on the square of the last thing in the binomial, and the square of 1 is 1. So there's the initial sum of cubes factorization taken care of there. Now, when you look things over here, you've completed a difference of squares factorization here and a sum of cubes factorization there. What you want to do now is look at the factors that those completed stages have generated and see if anything is further factorable in any of that stuff. Now, when you look through here, again, the -5, it's done. That was done from the beginning. X squared plus 1 is a sum of squares, but remember that sums of squares don't factor any further over real numbers. So that's a completely factored form. You can't do anything to break that down any further. But now look at this. X squared minus 1, that's a difference of squares now, where the two things being perfectly squared, as you can see, are x and 1. So that's going to admit a further factorization as a difference of squares. And if you look at the x cubed plus 1 here, that again is something that's factorable, because x cubed plus 1 is a sum of cubes, where the things that you perfectly cube to get x cubed and 1 are precisely x and 1. So you're going to have more factoring here. Now when you look at this thing, this trinomial x to the 6 minus x cubed plus 1, remember that a trinomial that comes out of a sum or difference of cubes factorization is never itself any further factorable over the real numbers. So this trinomial, x squared minus x cubed plus 1, came exactly out of this sum of cubes factorization, so it's not going to factor any further. So that's done. In terms of things that are further factoring, then we have to take care of this difference of squares here and this sum of cubes here. So if we do that in a final stage here, there's the -5 that we pulled out in the beginning. There's the unfactorable x squared plus 1. But now we've got this difference of squares to handle, so x squared minus 1 will factor as the sum times the difference of the things being perfectly squared, so that gives you an x plus 1 here, times an x minus 1, the sum of the things being perfectly squared times the difference of the things being perfectly squared. Then the x cubed plus 1 sum of cubes factors down as its own binomial times trinomial. So again, note the pattern here. You've got a sum of cubes, so that sum carries through to the sign in the binomial part of the factorization, and it's bookended by the things that are being perfectly cubed to get you x cubed and 1. Those are namely x and 1. So there's the binomial part of that x cubed plus 1 factorization. It's just x plus 1. And now kick in the pattern to build up the trinomial part. So the pattern is the square of the first thing from the binomial, so that would be x squared. Opposite sign from the binomial, so that's a minus. The product of the two things in the binomial, x times 1 gets you an x, and then plus the square of the second thing from the binomial. Second thing of the binomial is 1, and 1 squared is again 1. So there's the trinomial that comes out of that particular sum of cubes factorization, and then don't forget to carry through then this x to the 6th minus x cubed plus 1 non-factorable trinomial that you got out of the prior sum of cubes factorization. So now when you look at everything here, things are fully factored now. If we just go through the list here, -5 is just a constant monomial, can't do anything more with that. X squared plus 1 is an unfactorable sum of cubes, so it's a sum of squares, so it's not going to factor any further over the real numbers. X plus 1 and x minus 1 and x plus 1 are just all linear factors, so there's nothing you can do to break those down any further. And then x squared minus x plus 1 and x to the 6 minus x cubed plus 1 are both trinomials that came out of a sum of cubes factorization, so they're not going to be any further factorable. So this is it. You've gotten everything as broken down over real numbers as you can get, and it's fine to leave it like this, but if you want, you can combine up these two factors of x plus 1 into a single factor raised to a second power. So a reasonable form of the final result then would be -5 times x squared plus 1 times x plus 1 quantity squared times x minus 1 and then just throw in those last two unfactorable trinomials, x squared minus x plus 1 and x to the 6th minus x cubed plus 1. And there it is. There's a perfectly viable final form for this factorization. We've taken care of all the factoring possibilities that there are there, and our final answer now isn't any further factorable over the real numbers.